Hi there, I'm Angus Montgomery, and today I'm going to be discussing strain energy dissipation in the Cascadia subduction zone. So firstly, I thought we should start simply by asking what exactly is strain energy. Strain energy can be defined as the elastic potential energy stored in a rock. It is being fed by the converging plates and can be transformed into permanent plastic strain. This transformation to permanent plastic strain is called strain energy dissipation. My talk today will discuss how strain energy dissipation applies to the Cascadia subduction zone, and towards the end I'll look into how fluids are thought to facilitate dissipation in the region. So now let's start with some background and take a look to see where the subduction zone actually is and what's going on down there. The Cascadia subduction zone lies just off the coast of the Pacific Northwest and spans more than 1,000 kilometres, stretching from Vancouver Island in the north to Cape Mendocino in the south. The subduction zone marks the boundary between the overriding North American plate and the subducting Juan de Fuca and Gorda plates. The denser oceanic crust converges with the lighter continental crust before subducting beneath the North American continent at a rate of 40 millimetres a year. A megathrust defines the boundary between the subducting and overlying plates, and with depth, this megathrust dissipates strain in different ways. In the crust, and particularly from the surface to around 30 kilometres depth, the megathrust is locked. The subducting plate behaves brittly here, and accumulated strain energy is dissipated via seismic events such as earthquakes. Here in the lock zone, destructive events are infrequent, with around 500-year recurrence intervals between megathrust earthquakes. Deeper down at the Moho boundary, however, the subducted crust slips stably and constantly due to increased temperatures and confining pressures. At these depths, the crust is increasingly ductile, and steady deformation means that there is no stress accumulation, favouring continuous aseismic slip. So now I've briefly described the upper and lower sections of the subduction zone, but what happens between these two end members? Well, it's important to realise that strain energy dissipation is non-binary, and in Cascadia, recent advances in technology have unveiled a family of previously unnoticed quasi-static slip phenomena. These accommodate strain dissipation down dip of the locked section, but up dip of the Moho. Quasi-static slip phenomena are now thought to be the principal mechanisms for strain energy dissipation in the Cascadia subduction zone. These quasi-static slip events have been identified from seismic and aseismic signals. Seismic signals typically include low-frequency earthquakes and non-volcanic tremor. Tremor events occur almost continuously in Cascadia and are essentially superposed low-frequency earthquakes that cause weak vibrations of the ground. Quasi-static slip is also evident from aseismic motion and is labelled slow slip. Slow slip is the episodic movement of the subduction zone, allowing the plates to slide past one another incredibly slowly. Slow slip events are so slow that seismic waves are not radiated, and detection of these events can only be made from highly sensitive GPS stations. To get an idea of just how slow the motion is, Segal et al. Suggests that slip in Cascadia is typically only 2 centimetres over a 10-day period. This means slip velocity is in the order of 10 to the minus 8 metres a second. Slow slip is an extremely important strain energy dissipation mechanism outside of the lock zone, allowing stored elastic energy to be released, particularly along the plate interface. An important aspect of slow slip is the regular pattern it follows. Every 14 months or so, slow slip and tremor coincide in Cascadia. This regular event is given the term episodic tremor and slip, or ETS for short. The impact of ETS is clearly shown in this figure from Joan Gomberg, which highlights the synchronous occurrence of slow slip and vigorous tremor. The plot shows how a GPS station in Cascadia is displaced in a sawtooth fashion. The site initially moves to the east for 14 months or so, then movement reverses, and there is rapid displacement to the west for 2 weeks of the year. These sudden reversals represent ETS events. During these 2-week periods, plate convergence is at its fastest, and more than half of all tremor events are recorded. Despite ETS events dissipating strain locally, it's thought that they incrementally increase shear stress in the lock zone, as stress is transferred up dip. This stress loading of the locked megathrust is why an increased understanding of ETS events is important. When stress loading eventually breaches the strength of the fault, a magnitude 9 earthquake is likely, and this will bring devastation to much of the Pacific Northwest. Back along the plate interface, an important feature is the high P to S wave velocity ratio, adjacent to ETS hypercenters. This high velocity ratio can be attributed to the presence of near lithostatic pore fluid pressures. The cause of slow slip isn't fully understood, but it is believed that fluids play an important role, and this is where the rest of my talk will focus. To understand how fluid accumulates at such great depth, we must focus on the subducting oceanic crust, which holds vast amounts of water. The crust releases this water through dehydration reactions as it is warmed down dip. As fluid is released, it rises buoyantly until becoming trapped beneath the impermeable overlying plate. This causes pore fluid pressurization. O'Day et al. Estimate a Poisson's ratio in excess of 0.4 at the plate interface, and this value indicates near lithostatic pore pressures. These high pressure conditions are known to lower effective normal stresses, shifting the Mohr circle to the left. This is significant as the Mohr circle is now much closer to the Coulomb fracture criterion and may even intersect it, resulting in failure and slip. But dehydration isn't the only process that involves fluids and affects strain energy dissipation in the Cascadia subduction zone. I'm now going to discuss two other hydromechanical processes that play an important role in Cascadia. These are dilatant strengthening and thermal pressurization. We'll start off by looking at thermal pressurization. In the upper parts of the plate interface, where seismic events dominate strain energy dissipation, fluid influences the evolution of the deforming rocks during earthquakes, when both the fluid and the rock undergo thermal expansion during frictional heating. This happens at a faster rate for water, however, than for rock, meaning fluid pressure quickly increases, lowering the effective normal stress and essentially weakening the fault, encouraging further slip. Segal et al. Shows through models that this thermal pressurization is a dominant mechanism when slip velocity is in the range of 10 to the minus 4 to 10 to the minus 2 meters a second. As we mentioned earlier, slow slip velocities in Cascadia are around 10 to the minus 8 meters a second. Therefore, although thermal pressurization does occur in Cascadia, it's unlikely to be dominant below the lock zone. Dilatant strengthening, on the other hand, is thought to be a dominating mechanism that drives slow slip. Dilatancy occurs in all compacted granular materials, including fault gouges. When slip and shear initiate, pores within the fault gouge dilate, creating an effective increased porosity, which lowers pore fluid pressure. This increases the effective normal stress and helps to inhibit further slip. Dilatant strengthening has therefore been suggested as a likely seismic quiescence mechanism, allowing any unstable slip surface to strengthen and stabilise. The rate and state dependent friction law can be applied in this case, and as Samuelson et al. Illustrate, dilation will create a negative change in pore pressure, resulting in increased shear strength via an increased effective normal stress. When these three mechanisms work together, we can begin to understand the role of fluids along the Cascadia subduction zone. And it's important to realise that while fluids released in dehydration may initiate slip, they also enable slip to be slow. Yamashita and Shubnell suggest that the prolonged nature of slow slip events can at least partially be explained by slip-induced dilatant strengthening and thermal pressurization. So in summary, the Pacific Northwest is home to the Cascadia subduction zone. Recent advances in monitoring technology have unveiled a family of quasi-static slip phenomena at 30 to 40 kilometers depth. Episodic tremor and slip events are thought to originate in this zone, where continuous seismic tremor coincides with aseismic slow slip every 14 months or so. The controls behind slow slip are not yet fully understood, but researchers are confident that fluids play an important role. There are two mechanisms thought to at least partially influence slow slip. Thermal pressurization increases pore pressure through frictional heating, destabilising slip. However, more often in Cascadia, dilatant strengthening acts to reduce pore pressure through the dilation of pores, stabilising fault slip. With increased knowledge on quasi-static slip events, we can begin to understand the extent of stress transfer onto the locked megathrust. Strain energy dissipation within the Cascadia subduction zone is key to this, and an increased understanding may even help to predict the next megathrust earthquake. Thank you for listening.